I will start this. This is the last lecture in our series here. So I will start here about talking about Hawking, and he is, of course, now remembered because he is. We just experienced. He died 2 weeks ago. He had this very special condition. Some kind of a motor neuron disease that consigned him to a wheelchair the most of his life. He got a diagnosis when he was 22 that he would live in a few days, maybe a few weeks or a few months, and then he surprised everybody by living to this March 2018, where he died in an age of 76. So that was quite amazing. He was consigned to this wheelchair, and there from where he was riding from the wheelchair, after this motor neuron disease, his motor activities started to shut down. So at the end, he only had a finger or two to write with, and then of course he had a computer that could somehow interpret what he intended to say, and he ended up writing a lot of different books, mostly introductions, or best known at least for his introduction to contemporary physics. And this is one of his most famous introductions we are reading. This is the one called A Brief History of Time. Later on he rewrote it and abbreviated into a book with the title A Briefer History of Time. So we will use the first version here. And here he's talking about the new cosmology. He writes his first version of his book in the 90s, and the second version in the 2000 something. And the first version he has that we were reading at some point, that there's a lot of things happening before, after that, and as a matter of fact, also after his second version. But we'll, anyways, we'll relate to some of the things that still stands as facts of the universe today. It is to speculate about the universe is, of course, a very old occupation. This is something humankind have basically done ever since the beginning of human civilization. They have tried to explain the universe, and they have tried to understand what is the earth, what are the heavens, and so on. The early Babylonians, for example, saw Earth as a flat, stationary plate, and the sky above was like sort of a dome that was moving, where the sun and the moon and the stars, they were attached, and then they were moving from morning to dusk. And this conception, as simple as it is, continued by among lay people for many centuries, well into the Middle Ages, and way beyond that too. As you have it in this woodcut you have to the right. I mean, I'll just say that you don't need to read all this. This is for me and for my students. This is not, but just follow my talking, and then the pictures here, then you're okay. But you have this woodcut that gives us an idea of the idea of the universe, the conception of the universe. A man, he is living on a stationary plate, and above him is the dome of the sky, of stars, where moons are attached, and where the sun also is there. And then he is a curious fellow, so he is trying to take a look at the other side. Nothing really meets him there, but the picture, of course, assumes that if he goes any further, then he falls down into an abyss of nothing. So that is the assumption here. The conception is logical enough, because we seem to know from experience that the Earth is flat and we don't fall off. We also know that the the sky is moving from experience, since all objects on the sky, they seem to be moving around us in half circles from morning to dusk, the sun, the moon, the fixed stars. But it doesn't explain all our experiences. There are some experiences we also have from daily life that is inconsistent with this fundamental and primary one. And that is, for example, the experience that everybody knew also in the ancient days, that when one observed a ship sailing outwards towards the horizon, then it seemed to disappear slowly and gradually under the horizon. So only at the end the topsail was left to be seen. And this is an experience that indicates that the Earth is not flat, but curved. Also the experience from seafarers that knew that from navigating by the North Star, that the North Star is not situated as a stationary point. On a flat Earth, it would be more or less the same wherever you travel on Earth, but they travel from south to north, and then they noticed that the North Star would be rising above the horizon line, sort of slowly and gradually, in a sense that could be measured. And then they could measure where on Earth they were. At the North Pole, it would stand almost zenith to them. This also indicates curvature and not a flat stationary Earth. The Greeks, they knew geometry, and they set up an experiment to see what they placed two sticks perpendicular to Earth, one in Athens, one in Alexandria, and then they tried to see on a specific date and time what the shadows were of these two sticks, and they saw it was different. If there was no shadow in Athens at one specific day and time, there might have been one in Alexandria. So they could measure the length of the shadows. It was casting, the sticks were casting, and then they could begin to understand, also measure that, and by simple geometry begin to measure, give a first estimate of what is the circumference of the Earth. So learned people, they begin to understand that the Earth had to be spherical and not flat. And this came out then as sort of in a model that Aristotle worked on first, and then later Ptolemy elaborated a model of the universe where we have a round Earth. So now it is round and spherical, but it is still understood to be in the center of the universe. And then we have sort of around that Earth, we have some orbits of different heavenly bodies they knew at this time. They had sort of 8 spheres that was controlling these orbits. The first sphere was then the sphere of the moon. The fourth sphere was the sphere of the sun. And then it went out into the 8th and last sphere, and that was a sphere of the fixed stars. Outside that, they didn't know anything about the universe. But it was sort of the universe in that time. It was a planetary system, and it was a model that continued for almost 2,000 years. It was taken over by Christianity. The theologists, they liked it for many different reasons. They liked it because, for example, Earth was in the center, and if we were the unique, perfect creation of God, it was only natural that we had the center position in a universe. They also liked the idea that everything that revolved around us was revolving in perfect circles. The perfect geometrical form was supposed to be the circle. So everything had to be perfect in that sense. Then the theologists, the Christian theologists, also liked the idea that beyond this boundary here, you have here, beyond the 8th sphere, there you had plenty of room for heaven and hell. So heaven and hell was not necessarily part of the realm of the earthly realm, but that was something then beyond, and there was space for that too. So the model served a purpose for for the Christian theologists, and they were so uh, insistent on this model that any kind of objections to the model was regarded as heretic. So people were very careful of not trying to question this model of Ptolemy. It was not that it didn't have flaws. People knew that, but these flaws were not really addressed. And if they were addressed, then they were sort of remended and repaired in somewhat clumsy ways. They were, for example, one had noticed that every movement in the heaven, in the sky, is not circular, it's not perfect. It was rather strange and zigzag and random. And how to explain that in a model that insists on the perfect circle? Well, that was not easy to exist, but one can do something with circles. One can add a circle to a circle, for example. One can add a so-called epicircle to the primary circle. So we have here, for example, Jupiter is orbiting around Earth, that's our center. And then we observe, of course, Jupiter from our Earth. And then you add a circle there. Let me just try to see if I find something here. If it works. Yeah, that works. You add this epicircle with the center in the orbiting circle. And then Jupiter are now allowed to move zigzag from our observation point, sometimes in this direction, sometimes in the other direction, according basically to this punctuated line here. So now you have a circular model consisting on one circle plus one epicircle that can explain zigzag movement. So the dogma of the circle has been rescued. And if one circle would not do the job, epicircle would not do the job, one could invent another epicircle on top of the first epicircle. So one had a complicated movement consisting of a major circle, then an epicircle, and then an epicircle. And they could, of course, be adjusted in all kinds of ways, their radius and their movements and their speed and so on and so forth, until they would fit that movement that was observable. So now one could explain these so-called strange movements, random movements. So this was why the Christian model it was maintained then. It was regarded as a heretic to discuss it. And therefore, although there was this problem, nobody really dared to. But there were problems, and somebody like Copernicus, then Kepler, then Galileo, they could see there were problems in it, because one of the problems is, of course, that you are adjusting. You are not observing you are not observing fact. You are adjusting a fact to a dogma. You cannot explain anything. You are just adjusting the fact to the dogma, and also, if you have this system of epicircles and epicircles and so on, then the model becomes all of a sudden very complex. And it's not that the model any longer can offer us any explanation. It only produces ever more complicated catalogs, where you have individual bodies in the sky that had to, whose movement had to be explained now with a complex system of epi and epicircles moving with this and that speed. So there was no explanation in it any longer. The theoretical explanation became sort of, you could say, adjusted to every individual body in the sky, and a theoretical explanation cannot be adjustment to each individual event. Then it's not theoretical, then it's not general any longer. So there was a problem there. There was somebody like Copernicus. He understood that, and he understood also that one could make a much more simple model that immediately explained everything. And that was if we, for example, placed the sun in the center of our universe, and then that let Earth rotating around the sun, orbiting around the sun, and then let our moon orbiting around our Earth. Then everything would fall in place, and we would have sort of a very neat and simple model that explained our solar system. This was a dangerous thing to do, so he wrote his ideas down in encrypted language, so the church would nobody would actually find it out before much later. But he was the first to understand and see that, and then came Kepler. He destroyed another idea. He destroyed the idea of the perfect circle because he understood that orbits was not actually circular, they were elliptical. So that was another idea that went down there. Galileo, he found then other facts, and he communicated the new ideas in Italian, the vernacular, and he was then finally persecuted by the church that would not hear more about this new theory, and forced to stay in some kind of a home arrest. But here we have sort of these two models. The last one we have down here, the page, is of course the so-called heliocentric. Sun in the middle, Earth here orbiting, Moon orbiting Earth. That is the one we know today, and we subscribe to today. And this is the one we, for example, see in many illustrations, where you see the sun here, and then you see the different planets orbiting, Earth as number 3. And then we have all the other planets here in our solar system. But if we look at the sort of history of cosmology, then we can see that our image of the cosmos has been expanding. Not just our cosmos itself, that has been expanding, but the image also. We start out with a very, very small cosmos in our imagination, just a stationary plate and the dome. Then we have our solar system, that's it. Then some people, they begin to understand that our sun is not the only star, there are other stars. And then we begin to have ideas about conception about so-called galaxies of stars, underestimating completely in the beginning the hugeness of our galaxy. Then other physicists in the 18th century begin to speculate that maybe even our galaxy is not the only galaxy. There are other galaxies. And then we begin to understand today that in our visible universe consists not just of 1 or 2 or 3 galaxies, but of 100 billion galaxies. Each of these galaxies containing 100 billion or so stars like our sun, with many more planets orbiting these hundreds of billions of stars. And that, moreover, we understand this is only our observable universe. So the universe we cannot observe, this must be much bigger. How big, we don't quite know. And then there are cutting-edge cosmologists that today speculate that maybe our universe is not the only. Maybe there are alternative universes with alternative physical laws. Maybe we live sort of on the grand scale, we live on something that is called a multi-universe, and not a so-called one universe. So the whole thing has become so big that when we measure distances now, then you cannot continue to measure in kilometers or miles or so, but you measure in light years. That becomes the measurable measuring route. So a distance that traveled by light in 1 year is a light year. It takes, for example, the light from our sun about 8 minutes to travel to Earth. So the distance from Earth to Sun is expressed in light years. Is 8 light minutes. Is 8 light minutes. The star that's closest to our sun is around. It takes 4 years for light to travel from that planet, from that star to our Earth, and that is around 4 years. light years away, so it is 4 light years in distance away from us. And here we have down here our galaxy as it understood now here, and you see that the sun is here in the outskirt in an arm of the galaxy that's called the Orion arm. The middle of the galaxy is here. This is a picture taken sort of from above, reconstructed, of course. You cannot travel outside and take a photo here. But so here we are, and here is the bulk, or the core of the galaxy. If you see it from the side, you will see something like that. A disk flattened out here, we are here, and then in the inner here we have the nucleus, or the core of the galaxy. This you can actually see on our sky today. I'll show you a picture. We can see from our point here, the sun, we can see inside into what the bulge of the core of the galaxy, or Milky Way. So this is the address in the universe. This is we live here, 3rd planet from the sun, and we live in the outskirts of the so-called Orion arm, and then we live in the Milky Way. And you see the distance here we are talking about. We are talking about a distance that is impossible to travel, because we are talking about distances in light years that are in the thousands and thousands. This distance here represents 10,000 light years. That means it would take 10,000 years to travel with the speed of light this little distance, for example, something from here to here. The whole travel across our galaxy is around 100,000 light years. So to travel from one side of the galaxy to the opposite side would take 100,000 light years. And that's the fastest travel we know. To send a radio wave out from our sun here, that travels the same speed as light, would perhaps reach some planet with intelligent life or a technique to pick it up, but it will take so many thousand light years that we could hardly expect an answer in sort of memorable future. Let's say it traveled 20,000 years, we say hello to somebody, and then the answer comes back 40,000 years later. So it would be a really slow motion communication. So maybe given there is so many planets, it's quite likely, and people think so, that there are actually aliens, other intelligent life than our own. But it's impossible to know, and it's impossible to contact them, because light is traveling very, very slow on a cosmological scale, although it is super fast from our perspective. We see another example of the distance here in the universe. Here now it's just, we don't even talk about here we have our galaxy Milky Way again. It's big enough in itself, one would think. But if you project it into what is called the local group of galaxies, then it disappears as a speck of dust. If you project that local group into what is called a supercluster, was our nearest supercluster, then that local group become a speck of dust. And then in that grand scale, you begin to see the structure of the universe. It's all the same. It has this spider web kind of structure. There is some condensed areas and some a little bit more naked areas. But it's always this spider web. Wherever you look, it's the same. So you say that the universe is homogeneous because wherever you look, it's the spider web you see. Everything is the same. And this has been a problem to understand that for physiologists and astronomers for a long time. Now they probably have an explanation. They have at least a suggested answer that I will not come into now. But this is the structure of the universe on a large scale. Of course, on a small scale, everything is different, but on a large scale, everything is the same. And here we have our what we can see, when we can see from the southern sky, here we see the Milky Way, the core. We see the bulge here, the nucleus, sort of illuminated by millions and millions and millions of stars that are stretching sort of across the sky. So there we are. So what is, there is some, with the speed of light, since it takes time for light to travel, it creates a paradox because, as I say, for us it travels so fast that we don't notice any delay whatsoever. It travels with approximately 300,000 kilometers per second. But if we, for example, look at something, a near object, like the sun, then the sunlight we see actually as something, it's something that has been emitted first. We see it with 8 minutes delay. So it's 8 minutes old. So we can only see things in the universe with delay. Not 8 minutes delay, because many things is much more delayed than our sunlight, surely. But the sunlight has this light speed of 8 minutes. So this makes Hawking make a thought experiment that's quite famous. You have this is his model here. We have the sun here, he imagines. And then we have, of course, our Earth at a certain distance from the sun. This is an axis. The x-axis is an axis for distance. So we are here at a distance of the sun. We are, according to the sun now, in the elsewhere. We cannot pick up. We don't know what happens in the sun here now. It's point 0. This is the axis for time. Now we imagine that the sun goes dark here now, point 0. We know nothing, and we will stay ignorant for a good while. At least we have to go up this time axis up to 8 minutes around here. Then we will enter the so-called light cone of the sun, and then suddenly it will dawn upon us that everything went dark, and we live in utter darkness, and the sun went out. But we have 8 minutes to be happy still, until we discover the disaster here that happened in the past. This idea, one generalized to everything we observe in the universe, everything. It generates, now this, what he has here, is a two-dimensional model. It looks like a triangle here. We have apex here and 2 legs of the triangle here. And the light moves here along the diagonal line. That's the fastest possible speed. If we have a 3-dimensional model, it will come to look as a cone instead. We have here the cone. This is a future light cone. If we send something out from here, our central point, then it will take time before it reaches something. We cannot reach anything outside here. That will be in the elsewhere. We can only reach something within the light cone. If, on the other hand, we observe something in the past, we observe light that has been traveling for many, many, many years, millions and even billions. So we see something, we see a light, the galaxies in the past light cone when we look at with our telescopes into the deep universe, we see galaxies that are just about forming, planets that are just about forming, because we look into something that happened in the very, very past, something that happens with the best of our telescopes. We can look around 12 billion years back. So we look at something that happened 12 billion years ago. And this is what we can see. But we cannot see, never, the present universe. We have no clue about this so-called hyper surface of the present. This is in the area Hawking he calls the elsewhere. We don't know that, we cannot notice it. This is actually the universe. This is the observable universe. This is what we can possibly reach by radio waves, for example. But the observable universe is a very small fraction of what this one here that stretches far and away, we don't know how far. but this we don't know. So we don't know the present universe. Of course, we will, when 12 billion years from now, then perhaps we'll know that one here, too. So this is the condition. We know the observable universe, and that's only a fraction of the universe. We cannot observe the present. Now the universe they have figured out, that was figured out already in the beginning of the 20th century, is expanding. And how can that come about? How do they know? It was a so-called Edwin Hubble that made the discovery. And it takes a little detour around another effect, something called the Doppler effect, that he knew and had been known since the 18th century. The Doppler effect we know too when it is applied to sound. Then it is sort of the phenomenon we know that when a car is moving towards us, then there is an increase in pitch, the sound of the car. When we walk down the street, we know exactly when a car is coming towards us. We can hear it. When it's passing us, then there is a decrease in pitch. And that's because in one case, the sound waves, they are compressed, so they are increasing, and in another case, they're stretched out. So they're decreasing, the pitch is decreasing. So we know that. That is a Doppler effect in sound. The same is the case with light. When a light source is moving towards us, light waves are compressed, and the light wave here is blue shifted relative to a certain spectrum here. The light can be broken up into a spectrum, and if light is blue shifted, something is pressed down towards the blue end. If it's moving away from us, it's red shifted, relative again to this spectrum here. Something is pressed up towards the red end of the spectrum. This something is something the physicists, they know, because if you break things light up in spectrum, then you will see certain absorption lines in whatever is emitting the light. That tells us something about the chemical composition of whatever is emitted. If we have a star, you get the light down from a star and you analyze the spectrum, then you see certain absorption lines, and that tells us something about the chemical composition of the star. That maybe because these absorption lines indicate is there helium here, is there hydrogen here, is there carbon here. It has different patterns, different codes, and these codes they know from laboratory. Every scientist they know these things, know this automatically, so they know exactly where they're supposed to be. And then they direct their telescopes against a star, and if the absorption lines is the same pattern, is sort of shifted towards the red end, then the star is moving away from us. It's so-called redshifted. It's not like the star is red or anything like that. It's just redshifted. The spectrum is redshifted. If it's moving towards us, it would be the other way around, and it would be blue shifted. So you can understand from analyzing this spectrum, you can understand whether a star is moving away or is moving towards us. So this was what Edwin Hubble, he then figured out. He was looking, he had some new telescopes in California there he could use, and then he wanted to study distant galaxies and supernova and so on. And he wanted to study them, and he wanted to, and he believed, sort of like one believed these days, in a stationary, unchanging universe. So what he expected was, of course, that there would be a random distribution of blue shift and red shifted objects. If it's stationary in the universe, then it should be more or less the same. Sometimes an object is coming towards you, sometimes it's moving away, and this would be random. What he actually observed was a surprise, namely that every object, every distant galaxy he was looking at was redshifted. redshifted. So that indicated, of course, everything is moving away. And that indicated again, the universe is expanding. It's not stationary at all. It's not unchanging at all. It's changing, and things are moving away. And not only could he figure that one out, he could also figure out that that there was a correlation between the distance of galaxies from us and then the speed by which they were receding. Their so-called recession speed. And he could see that, he could understand that correlation. He could sort of distribute his object here on this diagonal line, and then he would see if the distance was small, the speed by which they were receding was also relatively small. But if it was larger, the distance, the speed increased, and out there the speed was very, very high. So there was a correlation between the farther an object is in the universe, the faster it moves away, the faster it recedes. And there is some more mathematical models here, professional models here. This is then he could set up this diagonal line here. This was the correlation between distance and kilometers per second. And then he could calculate the slope of that diagonal line, and that gives him a constant, namely 72. So his constant is, Hubble's constant is, that galaxies, they move according to this constant 72 kilometers per second per a measuring a unit called megaparsec per approximately 3.5 million years. So, and in light years, 22 kilometers per second per million light years. So if we have here, now we will use the megaparsecs. If we have something that's relatively close to us, 100 megaparsecs, then it moves with a certain velocity, kilometers per second. And this is in the case around 70,000. It should be around 72. If we double the distance, we go out to something that is now 200 megaparsecs away from us. The velocity increase to the double. It should be around 14,000, as it is. And triple the distance, we also triple the speed. So there is a correlation here between distance and then velocity, recession speed. This was then also figured out. And then you have a less scientific model here. This is the so-called raisin bread. Sometimes people, they use a balloon. They have this balloon example, and then they blow up a balloon at some points, and then they can see something is expanding. Here we have a raisin bread, and we are this raisin here. We are the observation point here. And then you can see the idea applies. Here we have something that is close to us. It's 5 centimeters. And here we have another raisin that is far from us, 10 centimeters from us. When they recede, the one that's 10 centimeters farther from us recedes twice the distance than the one that's 5 centimeters from us. So double the distance, double the speed. This one moves 5 centimeters in 1 second. This one moves 10 centimeters in 1 second. Double the distance, double the speed. This is the correlation. This is just sort of a more pedagogical version of this one. It's the same thing. It's the same idea. So this is why they could now say that the universe is expanding, and then it looks as if it's expanding from us. Everything is moving away from us. In according to this given constant, Hubble constant, according to this given Hubble flow, as it's also called. But that's an illusion. Each point, wherever we would look from in the universe, it will look exactly the same. There's nothing that moves moving away from us. Then, of course, if that was the case, then suddenly we would be the center of the universe, and we are certainly no center of the universe. Then we will go back to the good old Christian theology, but there is no center. So if you move to point B here and make this the observation point, it looks the same. The universe is, from any point you choose as observation point, receding in all directions, as it's the same. So you will see the same wherever you place yourself. Then, of course, if you know this, then it's not too complicated to understand something that comes as a consequence of the theory, namely that if the universe is expanding, it has always been expanding, and then it must have been smaller 1,000 years ago, and 1,000,000 years ago, and 10 million years ago, and 1 billion years ago, and 10 billion years ago. This must be a consequence, and you can even, when you have Hubble's constant, you can even begin to calculate when it actually, the whole thing started. And then you have this idea of a singularity from where everything starts. We have a present universe here, then we say 5 billion years back, it must have been smaller, because it's expanding with a certain speed. Then we go, let's say 10 billion years back, it must have been smaller even, and much more dense, and much more hot too. And this you can also calculate the time when this happened, estimate the time. And then you can finally go back to point 0, to that singularity from where everything started, and that is the so-called Big Bang. That's what is popularly called the Big Bang. And this means that the universe is far, far from stationary and permanent. It has been extremely dynamic, and is still dynamic, is still moving, is still expanding. So we start from this Big Bang, which nobody is, of course, everybody is very interested in understanding what exactly it is, but nobody is quite clear about what it is. It is something that starts very, very, very quickly, and maybe not from something that is much bigger than a tennis ball. And then something happens. I'll not go into it here, but something happens, so-called inflation, that blow the universe up to enormous dimensions, and then it begins to develop, evolve into what we see today. The last thing I will talk about is the future of the universe, because there is also interesting explanation of that. One always thought, and in Hawking's first book he thought too, that we only had 3 different scenarios, and they all sort of involved decelerating expansion. You imagine sort of here, Big Bang is an explosion, and we know about explosions that it starts explosively, I mean very fast, and then it sort of fade down into it reverse itself into nothing. So one sort of applied that intuitive model, and then one saw different possible scenarios. We could maybe have started out in a Big Bang here, and then the universe will continue to expand and expand and expand, and then one point, that would be a culmination point, where it started to subtract, and go back into a big fireball they call the Big Crunch, where everything collapsed into nothing, and maybe a new Big Bang would be the result. That was the so-called Big Crunch theory. Or one could imagine that it started and expanded. It will continue to expand, but it will sort of level out, and then eventually it will just become sort of leveled. There will be no, it will just continue sort of to decelerate until found some kind of point of balance between the expansionary forces and the gravitational forces that forces it back to collapsing. Or it will just, the third possibility, it would expand and expand, but with decelerated velocity. Now today we understand that this is false. The real and true model is that it expands and has been expanding up till a certain point, a little bit before now, and then a little bit, 4 or 5 billion years ago, So, and then it has started to accelerate the expansion. Because there is other energies, there are other forces in nature than just what we know as matter and dark matter. This gives us gravitational forces, and that forces the universe to sort of pull together, to fall inwards, you could say. But there is also dark energy. That's an anti-gravitational force, and that pushes the universe outwards. Everything falls outwards. So we will see that the dark energy, has taken over now, and now it is forcing the universe apart. So it has an accelerated expansion that will perhaps go faster and faster. So it will, the universe will end up with an accelerated velocity and an accelerated speed, and perhaps tear itself apart, rip everything apart. First galaxies, they will be ripped apart. Then solar systems, they will be ripped apart. Then planets will be ripped apart. Then all kinds of objects will be ripped apart, and atoms themselves, they will be ripped apart. And in this model, the universe is becoming larger and larger and darker and emptier and colder and colder, until we have a huge universe but without any life whatsoever. And this is what we can expect. Not we can expect, it will take some billion years. Will we end in fire like in the Big Crunch here? No. We will end in ice. We will end in sort of a deep freeze of absolute zero. That's where the universe seems to be going. So that's where we will start, and so can you think about that. Yeah.